Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 1 for this week. And we're going to be talking about something called CAPE, and we're not going to be talking about Superman's wardrobe, but more or less an acronym, CAPE, which stands for Convective Available Potential Energy. Very, very fancy stuff, right? And this is a way of us assessing the amount of instability in the atmosphere, which is another term that we will define as we move along here. So just going to be talking about how these terms relate to thunderstorms and how we actually use them in real time in terms of forecasting the weather. So let us move on ahead here and talk about this stuff. First of all, CAPE is used to evaluate instability in the atmosphere. Now, what is instability, ask you, and here we go. Instability refers to an air parcel accelerating upward or downward, really, from its initial position. If air accelerates upward, then it usually leads to very, very strong updrafts and severe thunderstorms, but air accelerating downward can be a problem too. We'll get to that in just a second. So if there is acceleration going on, that means there has to be a force. You might remember the equation F equals ma, or force equals mass times acceleration. So if there's acceleration, there has to be a force associated with it. And you might be asking yourself, what is that force? Well, it is buoyancy, and you've all witnessed buoyancy in your life. One basic example is, does something float in water or not? If it floats, it's buoyant. If it doesn't float, then it is not. Now, if an air parcel is less dense than the air around it, it will become buoyant and will accelerate upward against gravity. If it is more dense than the environment that it's in, or colder, it will accelerate downward with gravity. And we see this with thunderstorms where you have really cold air at the top of the thunderstorm that begins to sink and it accelerates downward, and when it hits the ground it can't go through it, and so it spreads out, and you end up getting these downbursts that can create damaging straight line winds, which are an entirely separate process from tornadic winds. And this is why severe thunderstorm warnings are issued even if there is no suspicion that a tornado is present, because this negative buoyancy, if it gets strong enough, can create some very, very strong downdrafts and therefore some very, very strong winds once they spread out, or once the updraft spreads out at the ground. Okay, so meteorologists use something called a skew-T log P diagram, and it has those two elements in the title for this reason. First of all, the lines of equal temperature are skewed, hence the name skew-T. And so these are isotherms, if you will, that go all the way from the ground up high into the atmosphere. The diagram itself, I think, actually goes up to about 100 millibars, which would, be way, way up there. I think 60, 70,000 feet, something like that. So these are lines of equal temperature, or isotherms, if you will. And then the log P part of the title is used because the atmosphere's mass is not distributed in a linear sense, okay? What I'm going to do here is I'm going to draw in lines of equal pressure, or isobars, if you will, and I'm going to do them in 200 millibar intervals. So we start off at 1,000 down here, then we go to 800, 600, 400, and 200. So the same amount of mass exists between these two dotted lines as these two dotted lines, but these two are way farther apart distance-wise than these two, okay? So what this is telling us is that the mass in the atmosphere is distributed logarithmically. In other words, gravity is making it most dense near the ground, and then it gets progressively less dense as you go up. Now, mathematically, if you're interested or care about this, and we'll talk about that in a second, about what that actually means. But here, this is actual data. The darker line there is what the weather balloon in Greensboro this morning showed as it went up through the atmosphere. This is pressure down here along the x-axis, and I reversed the order because 1,000 millibars is near the ground, and then 0 millibars will be at the top of the atmosphere. And then along the y-axis here, you actually have the height in meters above sea level. So that dark line indicates how the mass was distributed, and then I, using Microsoft Excel, drew in a perfect logarithmic curve. That's what the dotted red line is. So you can see that's very, very close to what the weather balloon observed this morning. Okay, so let's just take a look at a couple of hypotheticals here, and let's say the pressure went from 1 millibar all the way up to 100,000 millibars, which if that was the case, we'd all be crushed to death. But the one thing about these numbers is that you can write these numbers in an exponential form on the left-hand side here. So basically, exponents refer to the number of zeros after the 1 if you're using 10 as the base for your logarithm. So there are no zeros after the 1 here, so 10 to the 0 power is 1. And then 1 0 after the 1, so that's 10. And another way of looking at this is 10 times itself. So here, 10 to the second is 10 times 10 or 100. 10 times 10 times 10 is 1,000, all the way up to 10 times 10 times 10 times 10 times 10, which is 100,000, or 5 zeros after the 1, okay? Now, what I want you to notice here is that the distance between 1 and 10 is 9. Then the distance between 10 and 100 is 90. Then the difference between 100 and 1,000 is 900. And then it goes up from there to 9,000 and then 90,000. So the distances between these numbers is getting bigger and bigger and bigger and bigger. But if you just look at it from a exponent standpoint, it's going 0, 1, 2, 3, 4, 5. The distance between those numbers is constant. It's 1. So one of the ways that scientists take a function that is not linear and transform it into one that is by using logarithms. And in this case, what you would do is replace all of these numbers over here, the height above, the height above sea level, okay, and then you've got the pressure down here along the x-axis. You would replace this with basically, keeps going ahead of me here, basically exponents, which instead of having that bigger and bigger difference in pressure as you go up, okay, then it's going to basically stabilize that and make the function linear. I hope that makes sense. I hope I didn't make that explanation harder than it needed to be. All right, so here is a skew p log p diagram, and we're going to do a hypothetical here where the temperature is 95 and the dew point is 70. All the temperatures on this diagram are in Celsius, so I had to do the conversion there. So this is, again, just hypothetically, what the atmosphere looked like as the weather balloon went up. And since the lines of equal temperature are skewed and are oriented like this, okay, from lower left to upper right, then any curve or plot that goes across those lines indicates the temperature is decreasing with height. Now, the dew point, what you do there, and can you see these little dotted green lines that go like this? These are what are called mixing ratio lines, and they're really the same as the dew point in the sense that it's just telling you how much water vapor is in the air. So you take the dew point and you move up along that mixing ratio line, you take the temperature and you move along the dry adiabat, and where they meet is called the lifting condensation level, or LCL, okay? Now, once they meet, then the air is saturated at that point. The temperature and the dew point are the same. And so then you start releasing latent heat. And so the temperature of that air parcel can no longer decrease at the dry adiabatic lapse rate, which, remember, are the lines that go like this, which are about 5.5 degrees per 1,000 feet. Now, because of the heat it's releasing, it's going to decrease at a much slower rate, and it's going to go up along these moist adiabats, these lines that you see here. So what happens from that point forward is the air parcel rises along the moist adiabat, and the area that is shaded between the air parcel temperature and the actual environment is called CAPE. And the bigger that CAPE is, the more buoyancy there is, the more acceleration there's going to be, and the stronger the updraft is going to be. Now, there can also be forces associated with wind shear that will add even more to the strength of that updraft, but we're just talking about the pure thermodynamic forces that are going on here. And because shear and CAPE are the two big ingredients for severe thunderstorms, you can have what we call low CAPE, high shear storms, where the CAPE isn't all that impressive, but the wind shear is, and it could still be a severe storm. Or you can have a low shear, high CAPE storm, where the shear isn't all that impressive, but the CAPE is unbelievable, and so you end up getting very, very strong updrafts due to the force of buoyancy. So you can come about this in a couple of different ways, but this is the way you would take a skew T log P diagram, plot the actual numbers from the weather balloon, and then say, okay, if an air parcel rises from the ground, how high up is it going to become saturated? And then what is it going to be its path from there? And how does that air parcel temperature compare to the environmental temperature? And that will tell you how much CAPE you have, and therefore the potential for a strong updraft and a severe thunderstorm. So I hope that makes a little bit of sense. And that's one of the tools that we use, especially during the summer months when buoyancy is a given on just about every day of the summer. Okay, that is it for now. There are your credits. That is the daily or bonus weather video, I'm sorry, for this Monday. The next one coming up Wednesday, and the next daily weather update coming up tomorrow. So stay cool, stay out of the updrafts, and we'll talk to you again tomorrow. See you later.